in this chapter, we need to start by reminding ourselves that population parameters are generally unknown, right? Remember that from the beginning of the semester? We had statistics and we had population parameters. And we said that population parameters were generally unknown. So, this whole chapter is about estimating the population parameter. All right, a population parameter. We're going to talk about proportions. We're going to talk about means. In the chapter, I think it talks about standard deviations. We are not going to talk about that. Okay, but that's what the focus of this chapter is. And so we start with this idea of a point estimate. Remember, our goal is to figure out what the true value of the population mean is, or a population proportion, or whatever. So a point estimate is really just a single value estimate of the parameter. For instance, if I talked about the average number of credit hours that students are taking here at Midlands Tech, I might say somewhere between, well, I might say, let's say 12, right? That could be a point estimate versus a confidence interval, which is an interval estimate of the parameter. Okay, so instead of just saying we believe that mu is 12 hours, we might say we believe that mu is between 8 and 14 hours. Okay, that's a confidence interval or an interval estimate of the parameter. Which one of these things do you think is better? A point estimate or an interval estimate? Okay, why would you say interval? Okay, you have a bigger window. It gives us a greater opportunity to capture the parameter. Okay, let's see if we can play this video, which I should have loaded. That was a lot. They did. I think he said it was close enough. Poor thing. So, okay, the point being, which do you think, I think his name was Lewis, would it have been better for him to have a dart or the rangefinder to capture the price? The rangefinder, okay? Even though we'll talk about some things, I mean, if the rangefinder is the same size as the range, well, that's not an interesting game, is it? So, you know, having a very large range, we'll talk about this a little more, you know, we could be almost certain to capture the average, but that's not really telling. But interval estimates are important. Now, I'm just going to give you a little bit of an idea about how these interval estimates are formed. We talk about the level of confidence. And so we start with usually the point estimate at the center of our distribution. Okay, and we'll talk about what the best point estimate is. But for a mean, it would be the sample mean. Okay, and when we get ready to form this confidence interval, we're going to take a certain percentage of all of the values around the mean. And that percentage is 1 minus alpha. Okay, 1 minus alpha. And that, you remember, we've been talking about alpha for a while. If I've got 1 minus alpha here in the middle, then how much do I have left over? If 1 is the total beneath the curve, then what's left over outside of that area? Not infinity. Yeah, right. Well, outside of this section where I've outlined it here. If we got 1 minus alpha here, then what's left over is alpha. Very good. Okay? And that alpha is going to be evenly split. And so this is where that notation that I wrote last week and said, oh, we don't have to write that yet. Z alpha over 2. Comes from. This one would actually be negative. Okay, so we're going to talk about that, but that just gives us a kind of general idea. If I wanted a 95% confidence interval, then basically there would be some z-values that help me define capturing 95% of the possible values around 1 minus alpha. Okay, and so that would give us our interval estimate for population parameter. General format of a confidence interval is the point estimate plus or minus the margin of error. Okay, point estimate plus or minus the margin of error. All right, so what's that margin of error about? You see that all the time, right? In elections and things like that. You know, we get a percentage rating for a candidate plus or minus so many points or whatever. That's the margin of error. It's the maximum likely distance between the parameter that we're trying to estimate and the point estimate. Okay, so you know, it's kind of, when we say margin of error, it's kind of like saying at most we're off from the thing that we're trying to target by so much. And we'll talk more about how we find that margin of error. But this idea of the confidence interval being the point estimate plus or minus the margin of error, that's really kind of key. Okay, except as we go and look at different parameters, then you know what the point estimate is and how we calculate the margin of error, that's going to vary depending on what we're looking at. Okay, I think that's most of our, well no, that's not quite all of our theory. Oh, some common critical values. That z alpha over 2, that's what we call a critical value, and that's going to become really important as we look in this chapter and also the next chapter. So some common critical values that you might want to look at. If we have a 90% confidence interval, okay, then z is going to be equal to plus or minus 1.645. May I look in your textbook? Thank you. Okay, and for 95%, yes, if we have a 95% confidence interval, then z is going to be plus minus 1.96. And for 99% confidence interval, it's going to be z equals plus or minus 2.575. Okay, so these are common levels of confidence: 90%, 95, 99 point, or rather 99%. And so it's worth it probably to memorize these values. But let me show you for at least one of them where these values come from. Let's say we've got a 95% confidence interval. Okay. Then we just said that alpha in this case is going to be what? How much do we have besides 95%? 0.05, right? There's 0.05 left outside in these two regions, and because it's the two regions, we split it in half. So we got 0.025 in the tail. All right, and so what could we use that we've talked about before to help us figure out what this z value is? Inverse norm. Very good. Okay, if we use our calculator, or if you wanted to, you could use the table, but it'd be easier on the calculator. It was 0.025. Okay, so we're going to do inverse norm, which is number 3, 0.025. And we get minus 1.96. Does everybody see that? Okay, so, you know, again, the values that we have here are common enough. The 90, 95, and 99%, they're common enough that it's worth it to go on and memorize those. However, you should also understand how we got there, in case we come up with an unusual level of confidence. For instance, let's say our level of confidence, we said plus minus 1.96. Okay, our level of confidence, let's say, is 87%, which is going to be right in the middle. Then in the tails, we have how much? 1 minus 0.87 is 0.13, right? We take half of that, which is what? 0.065. Very good. Okay? And so we could do inverse norm, 0.065. And it's minus 1.51, but it's symmetric. So we'd have minus 1.51 here and plus 1.51 here. Okay? All right, so that's how we use the table to find those values. Okay. So, like I said, we're going to be looking at 3 things, and I want you to start thinking about these 3 kind of categories, because they're going to be relevant to what we do in this chapter and the next. So we're going to be talking about hypothesis test in the next chapter. We're talking about confidence intervals in this one, but we're going to be doing it for proportions. This is kind of your flowchart or categories. Okay, we need to know how to handle proportions. We're going to talk about how to handle the mean when sigma is known. And then we're going to talk about how to handle the mean when sigma is unknown. Okay, these are basically the 3 categories of information that you're going to need to be successful on the next test. Okay, how to handle proportions, how to handle the mean if sigma is known, and how to handle the mean when sigma is unknown. Okay, we're going to start today talking about proportions. Okay, and then on Thursday we'll talk about the last 2. Okay, so constructing a 1 minus alpha % confidence interval for a population proportion, there is a formula. Let's see if I can remember it. It is p hat. We'll talk about what p hat is. Plus or minus z alpha over 2 times the square root of p hat q hat over n. Okay, that's the formula, but know that there's a button on your calculator that's going to help us. Okay, but we are trying to estimate a population proportion. So suppose I'm interested in the percentage of students here at the college that have a credit card. All right, that's a proportion type of problem. And so I might start with a point estimate. P hat is my point estimate for the proportion, and we find it by looking at x over n, where x would be the number of persons or items with the characteristic of interest, and we're going to divide that by our sample size. Okay? Once we get p hat, we already talked about how we find z alpha over 2. The level of confidence that we're doing this for would be given to us in the problem. And then q hat, who wants to take a guess, would be what? 1 minus p hat. Okay, and n, of course, is our sample size. All right? So that's pretty much it. I mean, you're going to find this to be a lot like riding a bicycle. Okay, I'm hoping. Okay, especially with our $100 calculators. Okay. So, for instance, it says a study of 74 patients with ulcers was conducted in which they were prescribed 40 milligrams of Pepcid TM. After 8 weeks, 58 reported ulcer healing. Construct the 99% confidence interval for the proportion of patients with ulcers receiving Pepcid who will report ulcer healing. Okay, so this is new. We can handle this. We're constructing a 99% confidence interval. What kind of confidence interval? We're doing this for a proportion. Okay, confidence intervals for the mean have slightly different formulas. They already told us, well, we said the formula for that is p hat plus or minus z alpha over 2 times the square root of p hat q hat over n. Okay, p hat for me is, how many people reported healing? So 58 over 74. Okay, this is a 99% confidence intervals, and proportion intervals are always z intervals. We're going to talk a little bit later about a t interval, but for proportions, we know already it's always z intervals. And since this is one of our common values, 99%, I already know that z is going to be what? 2.575. Very good. Okay. Times the square root of p hat, which we already said is 58 over 74. Okay, times q hat, which is going to be how much? I got 16 over 74 all over 74. Okay, I'm careful, and you don't even have to try to do it by hand. I'm just kind of showing you how the formula works, but I'm careful not to round. Decimals are very sensitive when we multiply them, and so if I round, that's going to cause things to kind of go out of whack. So that's why I left it as a fraction. Basically just said 74 minus 58. That's what was, 74 was the whole, so we had 16 left. Okay. All right, so just to show you that what we'll get later on the calculator is the same as what we get by the formula, I'm going to go ahead and put in 58 over 74. And here's something else you could do if you like to do things the long way. There's 58 over 74. And what I can do is store that in my variable p, or whatever variable you want to store it in. Is that p on 8? Okay, I can't see what that says. Okay, all right, there it is. So I've got p, alpha p, okay, and I'm going to say minus 2.575, okay, times the square root of alpha p times q is what? 1 minus p, and we're going to divide that by our sample size, which was 74. Okay, that gives me my lower end. And then if I do it again for plus, come on, no, I didn't want to go there. Stop. Alright, so we get 0.6606 to point, was it 907? Okay, that's our confidence interval for the population proportion. And what we say is that we're 99% confident that this interval contains the true proportion of people who would report improved conditions after taking this medication for 8 weeks. Okay, we believe that the proportion reporting improved conditions would be between 66% and 91%. Okay, do we know? Will we ever know? No. The only way we could ever know is to go and, give everybody the medicine who has the ulcer and then go back and see if they had improved conditions. We can't do that. Okay? But this is our confidence interval. Now, we don't say there's a 99% chance that this interval contains P. All right, we don't say that, okay? Because the interval either contains P or it doesn't. Probability always talks about future events. All right? It's really not interesting to talk about things that have already happened or kind of going on. It talks about future events. So once we have this interval, it's either in there or not. We don't know. Let me give you another way to interpret this. Let's say we'll go back to our example about students and credit cards. Let's say I send each of you out to get a sample of 40 students here at Midlands Tech, and you're supposed to ask them whether or not they have a credit card. All right? Then you come back and you construct your confidence interval to determine the proportion of students who have a credit card. All right? At the end of that, I would expect that 99%, if we did 99% confidence, 99% of the intervals would actually contain the true population parameter, and approximately 1% would not. That's what that level of confidence tells us. Does that make sense at all? Yes? No? Maybe? Not every point estimate is a good one, right? Remember last week when we did the little experiment, we had all of those different sample means? Y'all remember that? Okay, some of them were very close to the true population mean, 4.5, and some were a lot farther off. If I use 4.5 to come up with my interval, then I'm going to capture the population mean, right? It was a really good estimate. If I get one of those rare and unusual ones that's a long ways off, and I use that to form my interval, guess what might happen? I might miss the parameter. Does that make sense? So not every one of the intervals is going to capture the parameter, but we won't know. Okay? What we can say is that if we do 99% confidence intervals, 99% of the intervals constructed would contain the true population parameter, and about 1% would not. All right? Okay, so that's that. Now, what you really want to know is how do we do this on the calculator? Okay, so on the calculator, we're going to go back over to the stat key and learn some things about it that we did not already know. So we're going to go to stat, and we're going to be going over to this area that says tests. And there are all kinds of tests here. The test referred to hypothesis test. That's chapter 8, which we'll talk about probably next week. What we're working on right now are intervals, and that starts with item number 7. There's a Z interval for a mean, a T interval for a mean. We got 2 sample intervals for the mean. And then here's what we're doing. We're doing a 1 proportion Z interval. Okay, 1 proportion Z interval is what we need. So I hit enter on that. Okay, I went to stat, test, down to choice A on my calculator. I believe it was A, letter A. Did you keep going? Yes. 1 proportion Z interval. Okay, select enter. Alright, and so it asks us, what's X? Well, in our problem, X is what? It was 58. Very good. N is 74. Okay, our level of confidence is 0.99. And then we arrow down to calculate, or maybe if you've got that new operating system, you might have to do paste. This is difficult. There's the answer. Yeah. Just, well, to give you an idea, a little bit of an idea of why, what goes into it, how it's kind of calculated. But yeah, for most of us, I think we'll be using this. Okay. Now, there are some times, though, when I've had to go back to the formula. For instance, I can't quite recall the details, but sometimes it will give me, give us the percentage, the point estimate. And then it gives us a sample size. And your point estimate, to make this work, we had to put X in. Okay, which is the number of people or items that meet the characteristic. But somehow when you take the percentage and get ready to put X in, it doesn't come up as a whole number. X has to be a whole number. The calculator won't let you put in an X value that's not a whole number, because all of what we're doing here is based on a binomial distribution, which we found out in the last chapter is approximately normal under certain conditions. And so in that case, I had to go back and use the formula. Okay, so I did show you the formula in case you need it. You know, it could happen. It comes up. Okay, not intentionally, but sometimes it sneaks in there. Okay, all right. Something else I want to point out to you before we go on to the next one. This is our point estimate, and remember I told you the general structure is plus or minus 2.575. This piece is our what? What do we call this? All of this after the plus minus is our margin of error. Okay, this is my margin of error. Now, sometimes I'm sure my math lab is going to ask you about this. It's going to want you to find the margin of error. The calculator didn't exactly give us, I don't think, margin of error. It gave us that point estimate, 0.78378. That's what we would get if we did 58 over 74, but it didn't give us the margin of error. Okay, let me tell you how to get around that. All right, if we had a point estimate, p hat, okay, we added one margin of error, we subtracted one margin of error. So the width of my confidence interval is how many margins of error? 2, right? Does everybody see that? So if I only had the calculator and I didn't want to go through all these steps to calculate my margin of error, what I would do on the calculator is, once I see this interval that they gave me, subtract. Oh, I want it back. What was the number? 0.907 0, okay, minus 0.5, okay, minus 0.606052, okay, 2 sixes. All right, I'll just go ahead and hit enter, and then I'm going to divide that by what? 2. And that's my margin of error. That's what we would get if we looked at 2.575 times all of this stuff that we have right here. Okay, so the calculator doesn't give it to us directly, but we can figure it out just by finding the width of that confidence interval and dividing by 2. Okay. 2.575, that came from the fact that we had a 99% confidence interval. And remember we said that that was one of our standard values. And so I just kind of remembered that that was the value. Yes?
What was that we just found with the 2.5
That was the margin of error. Margin of error. We basically found the width of the confidence interval. So it was the upper end of the confidence interval minus the lower end. And then we divided that by 2. Because the width of the confidence interval is always 2 times our margin of error. Okay, let's look at another example. It says a Gallup poll conducted December 11th through 14th, 2006 found that 604 of 1,010 Americans own at least one pet. Conduct a 95% confidence interval for the proportion of adults with at least one tattoo. let's just say at least one pet, okay? That's probably how y'all feel when we go to the test. It's like, what? Pets tattoo? I don't know. That's a typo for sure. Okay. Yeah, let's just say pets, okay? That was confusing. Okay. All right. So anyway, what we notice here is that they've asked us to conduct this 95% confidence interval for the what? Proportion. Okay. So if we're going to lean on our calculators, what we need to identify would be X, N, and our level of confidence. Okay, X in this case is what? 604. N is 1,010, and the level of confidence is 0.95 is what we're going to put in the calculator. And so, whoa. Okay, we went to stat, over to test. I'm going to choose option A because I remembered that that's where I do my Z proportion interval. X is 604. N is 1,010. And my level of confidence is 0.95. Okay, calculate, enter. And so my 95% confidence interval for a proportion is 0.56778 to 0.62826. All right. Questions about that? Yes. Okay. All right. If for whatever reason it asks me about the margin of error, then I would try to do, let me write this down. So 0.56778. What was it? 0.62826. Okay. So my margin of error is 0.62826 minus 0.56778 divided by 2. Because the width of the confidence interval is 2 times the margin of error. We said plus minus. Okay. Okay, I got 0.03024. Okay, very good. You got to make sure you put those numbers in parentheses. That's why. The numerator has to be in parentheses. Okay? Other questions? Yes. Decimal places. Be able to match the answer on the test. Okay? All right, other questions? I know y'all seem disappointed. It's like, is this how it's going to end? The numerator in parentheses, and then divide by 2. Okay? What's that? Well, this number will always be larger. This is an interval of values. So we're saying we believe the proportion of people who own at least one pet is somewhere between about 57% and 63%. So our intervals always go from least value to greatest. That's right. Otherwise, it'll be negative. Yes. Okay. All right. Other questions? Okay. So you ready to try one on your own? Let's just make sure it makes sense. Consumer Reports Research Center survey of 427 women showed that 29%. See, this is what I was talking about. Of them purchase books online. Find a 95% confidence interval estimate of the percentage of all women who purchase books online. What I would do first is try to figure out what 29% of 427 is. Okay, 0.29 times 427 comes up to be 123.83. Okay, and this one came, I've got lots of examples, but this one came from our textbook in particular. So, what's that? I know we can't put that in. I would say let's go for it. We might have a little error, and we'll find out when we look at the practice test on down the road. But let's call it 124. All right, it's not going to be that off. I might regret this. Okay, we're going to stat, test. Okay, we're going to do one proportion, z interval, so that's alpha A. Okay, x is going to be, what do we call it? 124. N is going to be 427, okay. That sounds better. And our level of confidence, 0.99? 0.95, okay. And so there's our confidence interval. Okay, so we believe the proportion of women who purchase books online is somewhere between about 25% and 33%. Okay, so that's another project idea. If we decide to go with that, you could go around asking people, do you purchase books online? Yes. It possibly could, but the calculator gives that to us. So, okay, and then we can see right here how far off our p hat is from what they said it was. They said it was 0.29. We got 0.2903 or 04. So that's going to give us a little bit of error. We'll try to look at. Let me see if I can find this problem in my math lab to see how it's going to behave. Alright, so we're looking at this My Math Lab example to see if our trick will work. It says an online site presented this question. Would the recent norovirus outbreak deter you from taking a cruise? Among the 34,414 people who responded, 66% answered yes. Use the sample data to construct a 90% confidence interval estimate for the proportion of the population of all people who would respond yes to that question. Does the confidence interval provide a good estimate of the population proportion? Okay, so let's see. All right, I'm going to use my calculator. 66%. So we're going to go to stat, test. I'm going to use alpha A. Okay, and I can even do 0.66 times 34,014. If it gives me an error, then I know that that came out to be a decimal. It did. I don't think it's going to let me do it. Let's see. Let's see. It may let me go on and surprise me. It didn't let you do it. Level of confidence is 0.90. Okay, good. All right. So let's go back. I'm going to go to stat. I guess I have to quit first. Okay, go back to stat, test, alpha A. Okay, so I'm going to just call this 22,713. And now calculate. So, to 3 decimal places, I'm going to call this 0.656 to 0.664. And we're going to hold our breath. Alrighty. I want to check my answer. How do I check it? Okay, there we go. Check answer. Woohoo! So that seems like it works okay. Okay. Oh yeah, does the confidence interval provide a good estimate for the population proportion? No, the sample is a voluntary sample and might not be representative of the population. It was an online site that presented the question. So that kind of goes back to the beginning of the semester. We talked about what? Self-selected surveys. Okay. Yes, all the assumptions for a confidence interval are satisfied. No, the responses are not independent. Yes, the sample is large enough to provide a good estimate of the population proportion. I'm going to go with A. Yes? Well, I round it to the nearest whole number. That's what I would say. Alright. Okay. That went all the way back to the beginning of the semester. Okay, so that's how we can cheat the system. If we want to call it that. Alright, let's get back to our handout and see if we can't wrap this up. Without a problem, let's go back. For the interval that we came up with, I don't think we actually wrote it down. The last one for the consumer reports. Okay. So for this one, can we safely conclude that less than 50% of all women purchase books online? Why or why not? Yes, okay, the interval that we came up with did not contain 0.5. Alright, if we go back to that one, let me go back to it. Second quit. We hit stat, test, alpha A. That's the one where we had how many? What was it? 124 and okay, 427. All right. I did what? Okay. Stat, test, alpha A. 0.95. Okay. Alright, so looking at this interval, we believe the estimate for the proportion of women buying books online is between 24% and 33%. So the question is, can we conclude that less than 51% 50% of all women purchase books online, we would say what? Yes, 50% is not in our interval. Okay? Can we safely conclude that at least 25% of all women purchase books online? We'd say yes. Okay? Because 25% is well within the interval. I mean, if we estimate it, we would say this is from about what? 25% to 33%. Okay, very good. All right. So there's something else we should talk about, because like I said, with the rangefinder game, it would not be a good game if he had this huge rangefinder. That wouldn't be interesting. So same thing for us. I mean, we can be 100% confident. We can say the percentage of students who have credit cards is between 0 and 100. Okay? I mean, we'll be right. We know we're right. But that's not useful information. So a couple of things about confidence intervals. Big confidence intervals are not useful. All right? We usually don't like big confidence intervals. However, we do like a high level of confidence. If you go back and think about the values that we saw for Z, let me go back to that slide. If everything else stayed the same and we just changed the level of confidence, it's pretty easy to see that the width of the interval gets larger as the level of confidence goes up. Do you see that? Because the width of our confidence interval increases as the level of confidence increases. Okay? Because of, we can see that with these values. It's getting larger. However, if we increase sample size, the margin of error is going to decrease. Okay? So what people do in a practical setting is they already know the margin of error that they're willing to have. And they get the sample size that goes with that. All right? So I'm going to show you how that works. Okay? We need to look at the sample size needed for estimating the population proportion, P. And the formula for that, this is going to be something that we're going to need to remember, which I don't remember. Thank you. N equals Z alpha over 2 P hat Q hat over E. There's some squares in here. I think both of these are squared. Is that right? Okay, good. All right, so if we know P hat and Q hat, we also know the level of confidence. That's going to allow us to determine the Z value. And then E allows us to determine our margin of error. Both of those things would be given to us. Then this is how we would get our minimum sample size. Okay? If we don't have a preliminary study, then we estimate both P hat and Q hat to be 0.5. So that looks like Z alpha over 2 over E squared times 0.25. Okay, 0.5 times 0.5 is 0.25. That gives us the largest minimum sample size. Okay? So let's look at an example. A school administrator is concerned about the amount of credit card debt that college students have. She wishes to conduct a poll to estimate the percentage of full-time college students who have credit card debt of $2,000 or more. What size sample should be obtained if she wishes the estimate to be within 2.5 percentage points with 94% confidence? Okay? So we are looking for sample size. All right? And in this case, did they give us any information? Well, in Part A, it says a pilot study indicates that the percentage is 34%. So we can use the formula over here because we have a preliminary estimate. So we'll say n equals z alpha over 2 over e squared times p hat q hat. Okay, I wrote that a little bit differently, but it's the same thing. Okay, our margin of error is what? Okay, 2.5 percentage points, or in decimal, 0.025. Okay. And Z, we're going to have to determine. 94% is not one of our special values, so we're going to have to actually go and do a little work to figure that out. If we got 94% in the middle, how much do we have in the tails? 0.03. So we could use what on our calculator? Inverse norm. So second distribution, number 3, and then 0.03. Okay, we got minus 1.88. Doesn't matter about the minus part because we're going to square it anyway. Okay. P hat is 34%, so 0.34. Q hat is what? 0.66. Okay. Put that in our calculator. We got 1.88 divided by 0.025. Okay, I'm going to square that and multiply it by 0.34 and 0.66. Okay, we get 1,279. We can't have a fraction of a person, so we have to do something with that. We will always, always, always round up. If that had come up to 12, or let's say 1,279.00000001, I would round up to 1,280. The reason being is because I just said something really important, and that is if I increase sample size, margin of error decreases. Okay, you might want to write that down. If we increase sample size, did I get something wrong? What'd I do? Oh, okay. All right. I got so excited. Let's see. Hold on. Okay. Okay. Okay, let's delete the extra 8. That's real easy to do. Okay. Got him. Going to square him and multiply it by 0.34 times 0.66. Oh, I now got an extra 6. Okay. But anyway, the point is you always round up. Okay? Don't forget that point. What number should it be? 1269? Okay, 1269. All right, so our minimum sample size be 1,269. Okay? Oh, yes, I was saying that's very important. As sample size increases, the margin of error decreases. Okay? As sample size increases, the margin of error decreases. Okay? The second part of that is as level of confidence increases, the margin of error does what? Increases. Okay? To be more confident, we have to have what? A wider interval. So as level of confidence increases, the margin of error also increases. All right? And that's why we're doing this. We're forcing our sample size to be large enough so that we can have the level of confidence that we want and the margin of error that we want. Okay, the second part just says, well, what happens if we didn't have a preliminary study? Okay, then in that case, Yes, that's what happens. In that case, we say n equals z alpha over 2 over e squared, but we're going to say times 0.25 because we estimate both p hat and q hat to be 0.5. All right, z is still, what was it? 1.88. I remember now. And e was 0.025. Okay, squared. And so if we put that in the calculator carefully, that's right. Okay, mine is entirely messed up. What'd y'all get? 1414. Okay, I multiplied instead of dividing. Okay, 1414. Okay, and notice here that this minimum sample size is larger than the one that we had when we had a preliminary study. Okay, so if you don't have that preliminary study, you can count on having to get an even larger sample size.